leak because of, when they are logging the oil, this is a leakage. So that's the biggest leakage that we had. We have seen in Gulf of Mexico, like the last leakage that we had, right? But apart from that, because we rely too much on the sea mode of transportation, so that actually also leads to a lot of leakage of the fuel. That is the oil from the ships. That is one thing. Second thing, when there is what we call accident in the sea as well, right? Ships, huge ships actually, they carry large amount of containers carrying the oil, and if actually it hits another ship because of the collision, it also oil spill. And we have seen all these incidents happen in the past. Now the question is, sea is a very dynamic environment. It's not like land. It changes very rapidly and very quickly. Okay? How can we use this technique? First thing is to detect. Right? To detect. Once we detect accurately the spread of the oil spill, but it moves very fast. Right? How we can monitor it, where the spill is spreading, and how we can do modeling in terms of by bringing to a lot of these sea environmental parameters, so that we can give a trajectory of it. Right? That means every 20 minutes or 1 hour, how the spill is going to move, and ultimately where it is going to hit the shore, because it is going to hit the shore because of the waves. Right? So this is what actually are the problem statement in front of us. Okay. It's not working. Oh. Okay. This is also okay. This also. Okay. Now let's look at, every time we want to use the geospatial techniques, we have to look at the sensor. That means we have to look at the remote sensing data. So before that, we have to understand which kind of sensor is effective in terms of identifying the oil spill. Because it's a sea environment, right? We know the different type of sensors that we have. Very near infrared, which is very, very useful in terms of optical remote sensing. Then we have thermal infrared as well. Okay? But there is also called passive microwave, and there is also called active microwave. Passive microwave means, who knows about the difference between passive and active microwave? So passive microwave means it doesn't have its own source of energy. Okay? So in this case, it relies on the natural environment as the way actually each object on the surface of the earth that is emitting the backscatter. Okay? So you just have actually a sensor that records, and mostly it is very valuable for sea ice thickness, application of water bodies, moisture content, all that. Okay? Then there is called active microwave also, that is called scatterometer. That means the sensor has actually a source which can actually emit the signal, hits the object, interact with the object, and the backscattering signal comes back. That is what we try to decode through sigma. Okay? Now, to look at what are the variables that we will be needing in terms of modeling of oil spill, pressure, current, upwelling, upwelling in the sea. Then you have the wind speed, wind direction, surface wave, internal wave, like sea current wave, right? And flow wave. These are the sea variables, parameters. And what I have mentioned in this particular table is that which kind of sensor that will be useful for detecting different types of variables, such as current, upwelling. Sometimes you can actually detect partially from the very near infrared sensor. But when you use the synthetic aperture radar data, that is very, very useful most of the boxes. As I mentioned in my earlier presentation, that on the lecture, that SAR data is very useful actually because it is very sensitive to the water. So water body always will be seen as a dark background. So anything on top of it, it can be easily identified. So ship detection, SAR is very useful actually for ship detection. Okay. Now, if you look at the oil spill turbidity, what this is a chart, right? Can you see? So now, if you talk about oil spill turbidity and segments, look, oil spill obviously there are different kind of process code. You have from 95, you have from 91, you have wheel, you have then what? Diesel, you have from 98 and so on. What are those? 91, 95? In India we use what? When you go and pour petrol in your car, 95. 95 is okay. What is that 95? Octane. So that means the content of the octane is 95%. Another 5% is mix. Mix of what? Ethanol, mostly ethanol. And then you may have what? Some other chemical compounds that is when the process of oil. Right? So depending on the type of oil, obviously, the texture information that will be reflected on the satellite image is going to be different. Also depending on the chemical composition as well. Right? So chemical composition, viscosity, right? So depending on all of them, they can represent differently on the satellite image. Okay, but anyway, SAR is also sensitive to that. We will see some examples here. For the detection, most important we would like to know the location of the speed, current, wind, and waves. These are the most important data that you need. Okay. Now, imagine for the oil spill contingency, how many of you actually taking this exam today? I have some questions. Okay. So, for the oil spill contingency planning, oil spill contingency planning means overall management of the oil spill. What you need, obviously, is not just one agency to be required to do this, right? Therefore, if you look at the disaster management committee, there will be many different kind of agencies and stakeholders who will be working together, right? And in sea conditions, obviously, it is very, very different. Okay. Now, let me show you one case study that I have done some time ago. Okay. This is Peninsula Malaysia. What you see down here is Singapore. You know Singapore is one of the largest ports in Southeast Asia. The country doesn't have any natural resources. The only income that they get actually from the trading. That is the what? The port. Having said that, again Malaysia also is very popular for trading as well. They have a very major port, two major ports in the western side. This is called Port Line. It's a very big port as well. Okay? And this is the only sea route that connects the Africa, Europe, with the Asia Pacific. That is why China is so desperate to control this South China Sea. Okay? Right? Because this is the major seaboard. Okay? And you can see what actually I have recorded here, which is the number of oil spill that has happened sometime ago. That means more number of cases should have definitely occurred by now. Okay? Plenty. Right? Here this part, not very far, it's about 40 kilometers. I think this is the nearest distance between Peninsula Malaysia and Sumatra Island. It's about 40 kilometers. Okay? So this is just a narrow channel. That is what we call Strait of Malacca Strait, which is one of the busiest causeway for sea route transportation. Okay? Like bringing all the goods that whatever you buy, the electronic items comes through that way. made in Malaysia, made in Singapore, made in Taiwan. All the electronic chip that you use comes from that. Right? That's the route that actually they did. Okay. Now I'll show you some case studies here. There is this oil spill that happened in 1994, February 16, and this is the backdrop. Actually, is the spot multispectral image. So it's a color image. Okay. The good thing is that not only clouds, only a little amount of clouds are here. You can see, and some dark patches that can be seen. You will be lucky if you can have actually a cloud-free image to detect the oil spill, and obviously the spill must be clear. Okay. This is radar image. By closing eyes, also you can feel that there is a spill. See the difference between the previous one. There are so many other kind of features also appears to be as oil spill. Okay. But in the case of radar, when you are dealing with a sea environment, it is pretty much very easy. That's the area. This is here actually is the Singapore. This is Singapore exactly. And this is the southernmost tip of Asia. The entire Asia that we have, the continent, big continent, that is the southernmost tip. Okay? And you can see here, these are actually all the oil spill that has happened. Okay? There are many cities and towns across this region, and there are a lot of economic activities that is also happening around. Fishermen, beautiful beaches, recreational activities, then tourism sector, and so on. Malaysia is known for tourism. Okay. Now, this is pretty easy actually to collect and process the data and do the mapping of the oil spill. But now, the spill is moving. It's not stagnant, right? Sea is very dynamic, depending on the current, wind direction, wind speed, etc. Right? So obviously, how much that actually you can rely on the manual digitization of the oil spill. So you've got to come up with an idea of automatic detection of this spill. Okay? So what we did, because we have temporal images, okay, this is the study area that I already mentioned, right? This is the Strait of Malacca, this is Sumatra, this is Java, this is Banda Aceh here, this is where actually the earthquake happened, and Kuala Lumpur is here. Okay, and this is Singapore. Singapore is a very tiny island. You can finish saying Singapore in a day. That's not much time. But I know India is still not going to Singapore. Okay. So now you can also digitize, but also you can automatize the process. You are taking it with the radar image. I'll show you what are the steps that actually we apply to detect the oil spills. See, this is actually, can you see? This is one case study where there was collision of two ships. And this is a tanker, you see? And this can be seen. And this ship actually left the oil spill. Okay, now, see. There is another type of image also that we try to use, that is called GIS. Okay, European Remote Sensing Satellite Data as well. Okay? Again, not that easy. Some patches maybe you can be clearly seen, but the pixel variation doesn't, it gets confused with other type of pictures as well, depending on the welding conditions and all that. That is why in the first table I showed you what sensors are available for detection of different type of features. Okay, you take wrong sensor and try to look at actually to identify a feature that is not being able to detect it. It's a wrong approach. Okay. Now, let's look at actually. So the Malaysian government wanted us to develop a system. It's called Oil Spill Detection and Management System. Okay? That means how we can detect the oil spill, automatize the process, also bring in the real-time data, model them so that we can predict after some time where the spill is going to move and hit the shoreline, so that they can take the necessary precautions for the mitigation activities. Alright? So we thought of producing different kind of products. So before we dive in any kind of project, it's very important to do your desktop assessment. Come up with the planning. What are the objectives that I am looking at? Then only you can write a proposal, right? An agency would always ask you, this is the problem that I have. Please come up with a proposal. You got to come up with a proposal. With the resources, smart way, whatever resources that is available to you within the object. Okay? Is that? So then we come up with the idea, what are the different kind of products that we can possibly produce through our system, if you want to design a system. First would be active disaster map. That means knowing the location of the oil spill. That's I already shown you. Right? You can take, let's say, some images, then we can automatize the process and you can detect the oil spill. And why we say active? Because that's active. And if you are taking actually multi-temporal data, you keep on extracting that information, at least those information you can deliver to the department. Okay? So what it shows, that is basically satellite image of features, so actual disaster event, location and extent, and geographic references as well. At least they would know where is the nearest town and so on. The next product that we want to produce is called trajectory map. That means predict the movement of the oil spill. Okay? And spread and coastal impact of the oil spill in the marine environment. Then also wanted to produce a map. Right? How? Provide early warning information for disaster mitigation and preparedness that can give you these classes and restrictions and manual risk. Environmental sensitivity index. This is something we would have thought about. Right? That is a risk map. That means what are the parameters, socioeconomic or values at risk that are sensitive to the impending disaster. Okay? Then we wanted to produce oil spill emergency response map. If you have the data, then obviously you would know 3 days in our head that if you are predicting that, okay, this spill is going to hit, let's say, a particular town, let's say Chennai or somewhere. So at least the authorities would be ready. They would be in the readiness to go and clean the area and how much of efforts that would be needed. Another one is once the spill has happened, the affected area. What are the areas that have been affected and all those things also be done. Alright? This is how you come up with different products. And how these products are going to be effective in terms of disaster management. Okay, remember that cycle, disaster cycle. Okay, so all these maps, they are basically addressing to different components of the disaster cycle. Okay? Okay, so this is the case study here, as I mentioned. These are the different products also I mentioned. Now let's go for data source. What are the data source? Obviously you have to rely a lot on the government data source, right? So based on the Department of Environment. So we wanted to get the oil spill locations if they have the record from previously, or because without knowing the record, how do you search when it has happened? What is the invention that you should look at when you want to do the processing as well? Right? So mostly we use the radar satellite. Different kind of software. Those days we use the PCI Geomatica because PCI Geomatica is very good in terms of radar image processing. Even I also use Tetra also. They have a radar suite as well. We have used. There is also another like Gamma. Gamma is a very, very powerful software as well, but it is highly expensive. Okay, you have it here. I have seen. Okay. Now, to detect the oil spill, these are various steps. So, you have to understand each and everything. It's a very complicated process, but essentially what we did, we took the 16-bit radar image. Okay? Then, big image, we create a subset. Just focus on the this area. Why? Why we want to process the whole data set will become very big? right? So now you know that these are the area where actually suspected oil spills you will through your visual inspection and also the location that you have, you just make it subset. So the processing time would be less of it. Then we do the histogram calibration. We know that this is one of the steps that we follow so that we can calibrate the histogram, right? I mean, you have taught that. I mean, you have learned that in your image processing classes, right? Digital image processing. Then there are different ways. You set those as the lookup table. Okay? You set what is that? Lookup table. Next step, what we did with the texture analysis. Okay? And to this, we use the angular second moment and different kind of filters when we started applying. Okay? In this case, I think we use gamma filter. It's a long time ago. Okay? Gamma filter. After that, we apply the K-mean unsupervised classification. I'll show you some of these steps to maps. Okay? Okay? We keep on, then we apply another type of filter. Again, we repeat the process until actually we get the desired result. Remember, any kind of research like this you are doing, it's not just everything that you know and you can do. You have to figure it out by trial and error basis as well sometimes. If some people have already done similar kind of work, they still have a reference to follow. But if you didn't have a reference to follow, then you have to figure it out. Right? That's what you call research. Research, go, get it done, it's not working, okay, try something else. Until you are satisfied with the result. Okay? This is the 16-bit image. Now, we just actually are focusing on the area that we masked out. We are not interested anyway in the other entire image, we are just interested in this part. Then, this is the histogram as you can see. Then, we did the calibration of the histogram. As you can see here. Then we did the texture analysis based on the angular second momentum. Then we did the filtering because we masked out all of the things. We only focus on actually our suspected oil spill target area. You can see that we masked out everything else which is appearing as dark. We just get this part. Then we apply the unsupervised classification. You can also apply, but you don't have to use very sophisticated machine learning based. You don't need 2 or 3 times. Backdrop is black anyway, right? So sometimes, because you just want to apply some hi-fi techniques, but doesn't make sense. Because your output doesn't require you to use a hi-fi technique. Sometimes a simple visual inspection also can do a good job without going for very sophisticated. You know, right? You have to be smart. Okay. Then we did it for all the images. You see these images here. You can see a lot of oil spills. Okay. Only we are interested in 2 classes: water bodies and then the spills, oil spills. Okay, and you can see that there are 2 classes. Right? Once we produce these, we did the vectorization of the image. Okay? Because then we can actually run it through the GIS Remote. Okay? Now we have the vector. Now overlay actually on the same image that is the source. It's wonderful. It looks now visually it's appealing, visually also very easy actually to identify where is the location of the spill. Okay? Now that I have done this, we can do the batch processing. If the spill is coming from the same source, because remember, if there are different type of sources, often different quantity, what you call type, the texture is going to be different, the viscosity is going to be different, the chemical is going to be different. Okay? Are you getting clear? This is how the oil spill actually does the map. Simple yet very effective. Now, I don't want to show this kind of curve. Right? When you are presenting also, that has to be good. Then what we did, Okay, this is the ArcGIS, we brought it to ArcGIS, then we produce a holistic activity cluster. Based on the information that I extracted, now you see, when I produce, this is what the GIS allows you to produce very aesthetically beautiful information. Okay, see we put here, we put the population centers, nearby centers, then we map also the coastal areas and the activities along the coastal areas, and then we just classify it into high pollution area, and so there are basically total spill mass, and then from the spill mass it has actually been spreaded because of the viscosity, right? So we classify it into three: spill mass, high pollution area, and total pollution. Total pollution area is the entire. Okay. Then we just provided actually some other coastal information like land use, mangrove, and so on, and the altimetry, so that easy to understand. क्या कर लो चोरी तो ना करो. What we are talking about after the MS-370, the Malaysian Airlines that we lost, right? We have done the entire LiDAR-based digital mapping of the some part of the Indian Ocean where no one has ever gone there. That area is called the dirt collection area. The entire oceans goes and then collects that, and the sea wells that it's huge, sometimes can go about 40-50 meters. So going with the ship there also is highly dangerous. Very close to the southern, like port, I think about 300-400 miles away from port. But because of this, because they suspected, maybe the Malaysian airlines would have landed there, so they did actually entire very detailed LiDAR map, which we didn't have any information before that. So through this process, at least we know now. Okay? Getting? See, simple information can be also presented very, very effectively. Now, I can make it more information if it is available, I can put more. See, I put actually this information and you can keep on adding. So for this particular, we developed actually a small plugin as well with ArcGIS. That's processing, automating the process and everything. Okay? ArcGIS allows you to do that. QGIS also allows you to do that, creating plugin. Now next product that we're going to produce is oil spill trajectory map. Okay? This is that is the sea changes very quickly. Sea condition changes very quickly. Now we have to do a lot of literature review to understand how the ocean behaves. Okay, how the sea condition changes, and what are the mathematical equations possibly that we can use to model it. Okay, so we come up with a simple yet a meaningful flow chart. We wanted ocean current simulation model, that means ocean current first we have to simulate first. Okay, then wind speed and wind direction also we needed because it keeps changing. For example, the speed is here. Now, if the wind speed is 120 meter per second, it's totally different than 30 meter per second. And let's say the wind direction at that time is northeast, so it is traveling this side. Okay, but now it has already shifted to northwest, then you start looking this side. So those informations are highly critical for you to do the modeling. Then we wanted the ocean current. Then finally we propose a oil spill drift velocity model to calculate the oil spill trajectory. Okay, I have to memorize anything or whatever. It's just that to showcase you how geoinformation technology, geospatial technology can be applied. Okay, so far so good. Okay. We model actually the ocean current simulation. Okay, for 24 hours, 48 hours in advance, 72 hours in advance. In this case, we use the Princeton Ocean model, POL. Oh, sorry, POL. Princeton Ocean model, which is a very, very popular model that especially the oceanographers they use it for modeling the ocean animals. Okay. So this is the tide elevation of the study area, and you can see that how the ocean current is being simulated for duration here it is 12.5 hours. So that means during this period, how the ocean current is changing. Okay? And this you can see the meters of current. Okay? Then we also did the simulation of the ocean current as well. Okay? Tidal current of the ocean. Okay? Then we did the speed trajectory. Given for a wind speed, let's say we keep the wind direction constant, 120 degree. 120 degree means where? What is the direction? Northwest, right? Now it's the first quadrant. Isn't it? No? Second. 45 degree. Sorry, 90 degree. Yeah, second quadrant. Second quadrant. Okay, so let's keeping the wind direction constant. Now, let's say assuming the wind direction change, not changing, staying constant, and the wind speed is changing 1 meter per second or 2 meter per second or 3 meter per second. You can see the location where it is going to hit the shore also will be different. That is not actually the sea dynamic conditions, right? Okay? You see that? And also the time it takes to reach the shoreline is going to be different. Okay? Alright? You see, this is here actually, I have put the information here. The simulation shows this takes about 780 hours. This shows around half, 135 hours to reach the shore. This takes about 200 hours, 230 hours. Are you understanding? Okay? Now, if I want to plot them, you can see the difference. All speed trajectories of different wind speeds. You see, 3 meter goes and hits here, 2 meters hits here, 1 meter per second hits there. This is very important actually for emergency planning. If your model is showing that it is going to hit here, and in actual case it goes and hit here, okay? Now similarly, if I change actually the wind direction, keeping the wind speed constant, okay? You see, totally is, instead of going to Malaysia, Peninsula Malaysia is already going now to Indonesia. You know, उधर better, but anyway they will be happy. हमारे पास नहीं है. Okay? So these simulations are also very, very important. Now, we did the trajectory simulation. You can see. So in oil speed breaks down on the water. The big chunk, slowly, it gets spread out. So it was a massive challenge that we had because it is very, very difficult actually to break down that particular time mathematically the source of the speed into different parts. Okay, from one source, breaking it down mathematically into different parts and then bringing in all these variables, wind speed, wind direction, ocean current, and tide conditions. It was very, very difficult. Now, this is what actually the Department of Environment was interested in. Yeah, that's why you are predicting right. know exactly. That's why we can predict also the what you call exactly. Those things are pretty much can be easily predicted. Because the moon is not running away, right? You know exact location of the moon. Pretty much in advance. That's not a problem. You know, if you closely look actually, this moon creates, basically the water comes up and the earth moves inside. This high tide and low tide phenomenon, that's what happens. Without moon, we are not finished. It would be very wobbly. Without moon, we are very wobbly. It is just like this. And also the rotation would start. Also, it would affect actually the rotation. The constant rotation that we have also because of the moon. And also the tilt is also there because of the moon. It's a blessing. Blessing. If you wouldn't have that 23.5 degrees tilt, you wouldn't have the weather system. Okay? No, it's like this. There are also planets in our solar system that is 1 degree, 2 degrees we have. So essentially what happens is one side is always, that particular person is always become very cold, other person will become very light. Because the gravitational pull of the earth is so heavy, although it is rotating, but one side you can never see, the dark side, which is very cold. And at any given time, you can only see one side of the moon. Right? How? The creation. Just the right balance. A little bit of here and there, you are finished. And also the distance from the sun as well. A little closer, you want, a little far, just about there. You know that moon is just part of that. Okay? Now understand? I'm just showcasing you something else, right? Now, see, this was the collision site, and we simulated what is the path actually, our spinning route, and when it is actually to the shore. Okay? There is a special software that we developed. Started working on that just for this particular purpose. Okay? You can see this is the location of this field and how in a real time it goes and where it is in the solar. Okay? Then you can produce it actually now. Now you have actually very dynamic, active simulation, and also you can produce a static map as well. Okay? At least all your efforts, resources, whatever you have, you can get it ready to mitigate cleaning of the sea and everything. Okay? Got me? Now, going to the next step is called risk assessment. What you can do now that we have, which is the most prone, so this can be considered as a hazard map aggregation. Right? Now, we have to bring in actually all the socio-economic variables, which can go into the risk assessment, right? So the most important aspects are like shoreline, socio-economic activities that is going along the coastline, biological activities like fishing or any other kind of biological activities, land use, okay? All those data that we brought in, obviously a lot of field campaign that we did as well. A lot of data is not available, right? We brought them in, developed the GIS database. See, these are the different types of ranking that we created. It's called environmental sensitivity index ranking. We classified into 1 to 10. Okay. For example, ASI1 is rocky headlands where for platforms are seawater. See, these things you can't do by yourself as a geospatial engineer. You have to get the feedback actually from the experts. So it has to be in collaboration with them. Otherwise you develop something that's a rubbish. You don't understand the domain. Okay? So finally you see we have classified Right? Can you see? There are different types of landings that has been just now mentioned, like fisherman village, there is harbor fish landing, then what is the nearest airport, what are the different types of activities that is happening, like aqua, coconut, then fishing activities, oil palm, all those things. Okay, and then we map it. This is no analysis, it is just an exposure based. Okay? Now, if you just want to bring in all the resources that is available in your GIS database, you can just produce them in order to say that this is what would be the emergency response time. Okay? Like what? How many boats are into cleaning activities? And then what is the nearest navy who can actually respond? Emergency response means in the case of emergency, what is the response the agency can be able to provide quickly? Okay? Then affected area map, that is I think is very simple. Once you do already all those processing activities, you can come to the policy. Okay, here display. We go to the pictures. Okay? Any questions? We have 5 to 7 minutes because we have to wrap up on time. Diffusion and dispersion. What is the difference? Dispersion of the particle. Where did it go? Where did it go? Breaking it down, right? No. So diffusion basically breaking the particles. That is not restored. And dispersion is spreading the particles. Okay. Spreading the speed is called dispersion. Then diffusion is breaking up actually the speed into one lump of speed. Now diffusing. Okay. Any questions you have? Or anything that you don't have time. I couldn't actually a lot of applications that are not great. Or maybe mineral potential mapping as well. You wanted mineral potential mapping? Yes, who wanted mineral potential mapping? You lost. I can show you one case study. Very quickly, 5 minutes. Okay? I need to search. Okay, any questions meanwhile?
Sir?
Yes, sir.
Sir, in this case, you have to start with the but along with the images, it comes like salt and pepper effect also.
Salt and pepper effect. Yeah. Yeah. Obviously, that you got to deal with. That is the problem with salt and pepper effect. Spectral. But there are so many ways that you can do it. You don't have to do that. Okay, quickly. You have already seen that application of landslide. It's the same process. Now you're going to understand that what is the input data that you would like to know. For example, we know known deposits of silver, or let's say gold. We know, right? Now if I want to do a predictive map for the entire country based on the known deposits where there could be a potential deposit that is hidden that we have not identified yet, as yet. Okay? What would you do? What is the input data that you do? Obviously, first thing is the known deposit locations are very important. Yes. What other data that you get? Come on, you ISM guys. ISM is known for mining. Yeah, ecology obviously. What else? What is the most important actually information activity? Geophysical survey, geomagnetic survey, right? Telluric survey. Those are the data that you need. Okay? So, I can show you the here. Look at here. It is the same thing that what I have explained in the case of landslide. Okay? You have all the spatial data collection, deposit data, that means known deposits, geological data, geophysical data, geographical. Obviously, it takes a lot of effort to collect this data, and also a lot of field data collection plus laboratory assessment, especially the geographical data collection. Okay. And then same thing, you have actually the dependent variables and the independent variables. Okay. So you do the modeling, whether you want to use frequency ratio, logistic regression, doesn't matter. Okay. So for example, this is a case study. Okay. This is in Korea. This has done a lot of work in Korea. Okay. So what you see here, there are different kind of deposits. Okay. And you construct actually the spatial database. You can see here deposit, and in this case the deposit is gold and silver. Okay. So altogether let's say 46 deposits. Then geochemical data, what are the indicators of the geochemical data? They have arsenic, copper, nickel, lead, zinc. Okay. Then they have geological data, which is the geology and the fault. Fault is also an indicator. Okay, and different type of geological lithology also post a particular kind of area. Okay. You take all these data, make sure the cell size is fixed, depending on what are the types of input data and the resolution cell. Okay. And then you have analysis. See, distribution of arsenic, distribution of copper. MO is what? Molybdenum? No. MB is what? No. MO is what? Molybdenum. Okay. Then lead, zinc, geology, distribution of fault. Okay. All this like how we prepared in the case of landslide. Okay. Also in the floor we did the same thing. Then then frequency ratio, right? Same thing you do, right? Take the known deposits as like landslide locations, and then you do the analysis actually, the tabulate area analysis, zonal statistics against all the variables in each one. Okay, you calculate the frequency ratio. Alright? So it is not difficult. See the number of deposits it shows of individual. And then you calculate the frequency ratio. See here. Arsenic. How many pixels in individual? There are 10 classes. Quanta. Percentage of domain, because there are 10 equal area almost. Number of deposits. Okay. Percentage of deposit. And then you calculate this divided by this actually becomes the frequency ratio. Right? And then you take this, make it an integer, reclassify your input data. Value there actually when you do that assessment. Okay, take this and reclassify your input data, and then bring all of them actually to the raster map calculator, and then you produce your